I said last time I wouldn't store the vector of distances in the KD node, and the more I think about it, I'm not quite sure how I'd do it without storing them in the KD node, because I have to put it in this priority queue, and it would seem to get lost if you don't do that. So I just want to state that so I'm not misleading anybody. But I'm sure the details will work themselves out when you code it up, because that's what coding kind of does, is it forces you to make everything line up in your head. Because if you don't, it's not going to line up in your code, and if it doesn't line up in your code, it doesn't work. And therefore, I think that's why coding's so effective at making you learn. I had started making this chart, and I didn't bother saving the chart, so just use your memory and pretend there's a nice chart right here in this big blank spot. And some of the things we had talked about were how to use KNN to do document recognition. So here I'll fill in the parts we're talking about. KNN sparse vectors. Okay, we had talked briefly about how if you're doing distance, you can very well find the distance between a point and a line, or a plane, or a hyperplane, or whatever, right? The problem is, the more missing values there are, the worse that distance becomes, because the distance between a point and a line, well, it might be that, but it might have been that instead, or it might have been that instead, right? Because we don't know where on the line it actually is, because the value that specifies this vertical position is missing. And if it's missing, well, we can conservatively say the distance is greater than or equal to this distance. We can add a penalty in which we say, okay, it must be about that distance, but we don't really know what we're doing. We're kind of fudging it, and that seems to be bad. Suppose now your document representation is bag of words, or something like that, where you have an aardvark and angle and amplitude. Uh-oh, that comes before angle. I'm out of alphabetical order now. And it goes all the way to zix or something like that. Isn't that a word? Something like that. Okay. And suppose in your documents, document 1 contains the word angle 3 times, and this word 3 times, and that the word zix 1 time, because it's a document about zix or whatever that is. Most of these words it doesn't have. This other document has a 2 and a 1, and it also has the word zix in it, because there just happen to be so many documents about that thing, and etc. The thing with this particular representation is it is very, very sparse. Suppose you used KNN on this type of a model, how would it do? I think you'd all predict bad, right? And the reason it would be bad is because all of these missing values, if we assume conservatively that there's 0 distance between the missing values in this one, we're going to say, hey, document 2 must have a 3 here because that one does, when we're comparing them. And when you were comparing to, say, document 2 and 3, then you'd say, oh, document 2 must have a 7 there because document 3 has a 7. What's the truth? Well, none of it is. So another thing you could do is fill in all the missing values before you do the comparison, if you want. For example, you could take the average in each column, fill in all the missing values, then do KNN. That's one thing to do. People do that. There's something that seems to work a little better, and that's to use a distance metric that's known to work well with sparse vectors. Anybody know of any? Don't expect you to. I'm just throwing that out. Okay. So actually, just for completion, let's write some formulas up here. So Euclidean distance is, I need a sum symbol. Let's see. That's going to be too sloppy. Let's go. Copy and paste this and flip it. Hey, that's a pretty good sigma, isn't it? I could clean it up a little, but we'll call that good. Sum over I of x sub I minus, let's see, how do you write this? X sub I minus y sub I, we'll need some i's and a squared. We'll need some parentheses too. And now I need to move stuff around. I down here. Then we'll take the square root of the whole darn thing. There we go. Is that Euclidean distance? Great. Okay. Now let's look up cosine. Let's do Pearson's first. Pearson correlation. Okay. Do you know what correlation means? Suppose you have two variables and you ask the question, how correlated are these variables? 99% of the time when people ask that question, they're referring to Pearson's correlation. There are multiple ways to evaluate correlation, but the idea is, well, it's expressed well in this chart. See these line-y things? Those are highly correlated, because if you know where you are on the x-axis, you also know where you are on the y-axis. So that's correlated. All these pictures down on the bottom are examples of uncorrelated variables. And they've taken the advantage of the idea that Pearson's correlation only measures linear correlation. So it's as if you do linear regression, and if you get a line and it's not straight but has some diagonalness to it, then they're correlated. And all of these pictures down here on the bottom, if you do linear regression to it, there's equal pole in all possible directions, therefore you can't tell where the line's going to fit to the data. These Gaussian point clouds up at the top, you can see on the far left that's perfectly correlated, because if you knew x, you'd also know y. In the middle, you see there's a 0 there. If you know x, that tells you nothing about y. And if there's a little bit of correlation, then you know something about it. At an intuitive level, you get Pearson's correlation. Great. Well, how do you compute it? Like this. You go to Wikipedia and you Google for Pearson's correlation, then you scroll down and find the equation, and there it is. Let's see. I like this one a little better. It's a little easier for me to read. So let's look at that. Here's what it says. E is expected value. What does that really mean in math? How do you code up a big E? What that means for coders is average. So what you're really going to do is there's this variable x and a variable y, and by variable that means there's n points that have been sampled, and this is your data set. So we're going to iterate over all the samples in the data set and sum them up and then divide by n, and that will give you the average there. What do you suppose a mu is in reference to? This is the mean. Another way of writing mu sub x is expected value of x. So sometimes you could see this equation with e of all that stuff, and then inside of here is e of x. And that can be very confusing. But mu sub x here is just the average of x. So we're going to run through your whole data set and compute the average value for x. Then we're going to subtract that from all the x values. See what we're doing here? We're basically taking your data and shifting it so that it's centered around the centroid. So all we're doing is shifting x around the centroid, shifting y around the centroid, and then for every point, we're going to multiply them together after they've been centered around the centroid and compute the average of their products. And finally, we're going to divide by sigma x and sigma y. What do you suppose that is? That's standard deviation. So the way I would usually compute that is, after I've computed the mean, then I'm going to run through and see how much each point differs from the mean. So I'll take x minus mu sub x, run through all the points, divide by n. Run through all the points, square it all. When I'm done, divide by n. That'll give me the variance of x. Then I'll take the square root of the variance of x, and that gives me sigma of x. Okay, so I'm hoping now, having seen this formula, code has been forming in your head such that you could actually make a computer do that equation. Any questions on how one would do that equation?
So
Yeah.
when we run into categorical values, how do we deal with like mean or standard?
That's a darn good question. I'm not sure Pearson's correlation coefficient has a built-in mechanism for handling categorical values. So it's one of those cases where you sort of have to just have some experience and you hand wave it. How would I do that? I don't know. I guess if we're doing some kind of Hamming distance, we can assume they're already centered at the mean. Just kind of ignore that minus mu sub x. And 0 times 1, that's a 0, and 1 times 1 is a 1. So it's going to do something. Basically, when they're the same, I don't know. I'm betting if you substituted Hamming distance right here, and you just assumed the deviation was 1, maybe it would do something reasonable. I guess I'd have to fiddle with it and think about it. I feel like Hamming distance wouldn't totally screw up Pearson's correlation coefficient, but it wouldn't be Pearson's correlation coefficient anymore. It would be your own hack job of the equation. Change what? Yeah. I guess the ideal thing to do is to have some intuitive knowledge of how different your two categories are and plug that in here. Or rather, in this case, how correlated the two values are. And they're kind of different concepts to the point where I don't think anybody's ever really even produced an answer here. Another approach is you take all your categorical values and you represent them in some continuous form. And then everything's continuous, and then you do Pearson's correlation coefficient. So you're really eating the weirdness at some other step in your preprocessing phase. Yeah, so a one-hot encoding is what I do. So let me describe what that means. Suppose your categories are cat, mouse, and dog. For no good reason, just because I picked those categories. We can, if we want to represent these as 1, 2, and 3 in a single value, right? But then weird stuff happens. For example, suppose you have 500 examples in which the label is cat, and 500 examples in which the label is dog, and 1 example in which the label is a mouse. And then you average it all together. On average, it comes out to 2. And then you say, with certainty, I have 100% certainty that the next sample I draw will be a mouse. And yet, that's the dumbest thing you could possibly say, because experience has shown you there's a lot of cats and a lot of dogs and very few mice, right? Okay, so this representation is bad. This doesn't work very well, even though this is what people like to do, is enumerate their categories. A better approach is what's called a one-hot representation, where you do this thing. You say cat is a 1, 0, 0 vector, mouse is a 0, 1, 0 vector, and dog is a 0, 0, 1 vector. You see this? Can everybody recognize the identity matrix here? Okay, why is this any better at all? It's kind of just saying the same thing, right? Well, the difference is we're giving an orthogonal dimension to every single category. Because they're different dimensions, they're not correlated, which is actually a very highly relevant thing to bring up while we're talking about Pearson's correlation coefficient. Suppose we now have 500 examples of cat, and we see 500 samples of dog and 1 sample of mouse, and we sum them all up. What does our distribution on average look like? Well, it's going to be something like 0.499, 0.001, and 0.499. And so if we say, what is the next sample we draw going to be? Well, this distribution gives us a very clear picture of what this next sample is probably going to be. We're going to say, well, it's probably a cat or a dog. It's almost certainly not a mouse. And that's exactly consistent with the example I just gave you. Therefore, this one-hot representation is a pretty good thing to do in many cases. I like to say these are continuous values. Now they're not. They're always 0 or 1. But after we start averaging them together, they start getting really continuous, right? Therefore, I can say that this vector of 3 values is kind of like a continuous representation of this one category. And therefore, if I take all my data and I convert all the categorical values to a continuous one-hot representation like this, then I do Pearson's correlation coefficient, then I can pretend I'm only working with continuous values, and it kind of works. It's not true correlation anymore, but it seems to do a pretty reasonable job, and I think that's a good way to do it.